configurations, or more simply, the shape of the industrial manipulators. We can also consider to refer to this as the kinematic classification, as we're going to look into how different industrial manipulators move without paying attention to the forces that are required to make this movement happen. So, a manipulator is a machine in which the mechanism usually consists of a series of segments jointed or sliding relative to one another for the purpose of grasping and/or moving objects, pieces or tools, usually in several degrees of freedom. In order to do that, the system or the manipulator consists of links, which are rigid bodies, and joints, which enable the relative movement between the adjacent links. The most two commonly used types of joints are the ones that allow for translational or rotational movement. The prismatic joint is the most general one translational degree of freedom joint, colloquially also referred to as sliding joint, and it enables translational linear motion between two links. Then there is the revolute joint, which is the most general 1 degree rotational freedom joint, colloquially referred to as hinge or pin joint, and it enables rotational relative motion between two links. You can also see that those are used in order to designate what kind of kinematic and industrial manipulator to use. For example, the Cartesian robot, which we usually refer to as machine tool in this lecture, has a sequence of PPP, that is a stacked prismatic joint. For a 3 degree of freedom machine tool, that usually relates to a movement in X, Y, and Z direction. A principal type of this machine tool can be seen here, and its workspace corresponds to a parallel pit, or more commonly, a rectangular parallel pit. Then we need to consider that we have in this case 3 degrees of freedoms on the manipulator, meaning that you can move the machine in X, Y, and Z. And this results also in 3 degrees of freedom of the object to be manipulated, meaning that the machine can reposition any object to any X, Y, and Z within the workspace. The workspace, which is also called working space, is the space which can be swept by the wrist reference point, increased by the range of rotation or translation of each joint in the wrist. For the Cartesian robot or the machine tool, there's one further thing to remark, and that is that it usually has a bigger footprint than the workspace that it provides, as it is built around the actual workspace, while for the rest of the manipulators that you see in this classification, it is actually the opposite. That is, you will find that the manipulator is placed in the center and the workspace that it can sweep around itself is significantly bigger. The next type of manipulator is a cylindrical robot, which has an RPP configuration, where we have a rotational prismatic, which means that the base can rotate about its own z-axis, resulting in a cylindrical workspace. And not only does this robot have the same degree of freedoms as the machine tool with respect to actuatable degrees of freedom, so you can rotate and then move it up and down and out and in, but this also results in more degrees of freedom on the object that you are manipulating. Because now you can put it into all the positions within the workspace, but you can also change its orientation within the workspace, as its orientation will shift accordingly with the rotation about the z-axis of the cylindrical robot. Then there are spherical robots, which employ rotational prismatic joints. This means that it can rotate about the z-axis, it can rotate about its x-axis, and then it can move in and out this arm, which results in a spherical workspace. And once again, while it has 3 actuatable degrees of freedom, this results in 5 degrees of freedom on the object to be manipulated, because once again, with the 2 rotations and the translation, you can put it into any positions, but now you can also change 2 degrees of its orientation. So you might think of Euler angles, which is represented in terms of the rotations about the x, y, and z axis, or the rotation about the z, y, z axis, which is a common way to express this. Cylindrical robots and spherical robots are robots that you will no longer be able to purchase from the big robot manufacturers around the world. Those used to be produced between the 1960s up until the 1990s and then have faded out because the value added by the other types of robot is generally bigger. Nevertheless, you actually might find some of these robots still being in use in the facilities of the industrial partners that you go to because they have been purchased in the past. One additional aspect when it comes to actuatable degrees of freedom and the degrees of freedom of the object to be manipulated. If you want to take a more analytic approach to this, you might want to look up the Chebyshev-Gröbler-Kurzbach criterion, which determines the degrees of freedom of a kinematic chain, that is, a coupling of rigid bodies by means of mechanical constraints. The SCARA robot with an RRP configuration. SCARA stands for Selective Compliance Assembly Robot Arm, and it is a robot which is used in pick-and-place applications that have tight tolerances for the insertion of the object. The SCARA robot has compliance in the horizontal plane, and it can, so to say, wiggle itself into the right position to insert an object. Here you can see how a SCARA robot is used to pick-and-place batteries. And as said before, so the robot has compliance in the horizontal plane, meaning that if it were now to reinsert those batteries into those slots which have a tighter constraint on the placement of the batteries, it would be able for the robot, in case that it actually hits the sidewall, to wiggle itself into position, rather than consider this to be an impact. So the SCARA robot is the last robot for which we will actually find that we can describe it simply by a 3-letter abbreviation because it has 3 actuatable degrees of freedom. The next robot that we are looking into is the articulated robot, which has a solely configuration consisting of rotational or revolute joints, and it usually has 6 or more of these, which results in a spherical shape, and it results in 6 degrees of freedoms on the object to be manipulated, meaning that it can not only put it into any position in its workspace, but it can also put it into any orientation in its workspace. And that is why serial articulated manipulators are that commonly found in a wide range of applications. Here you can find an application of industrial manipulators in the manufacturing of automotives. Starting from pick-and-place applications, to the dispensing of glue, spot welding of the body in white, or inspection of the car body. As said, these robots come with either 6 or more degrees of freedom to be actuated in the manipulator, and what this means we're going to look to on the next slide. But before we do that, we are also going to look into delta robots and dual arm robots, as well as the general classification into PKMs and SKMs. But let's start with the delta robot, which is the first parallel kinematic machine that we're going to look into. And here it isn't possible to give a simple letter abbreviation because those joints or these 3-letter abbreviations, as we said before, you read them from the left to the right, and you read them correspondingly from the base to the mechanical interface of the manipulator. And here you have a serial chain of those joints, meaning that you have only one ray to read those letters and start from the base and arrive at the mechanical interface. For parallel kinematic machines, this isn't possible because you have several actuators acting on the same link, meaning that there is no simple way how to read yourself in terms of actuators from the bottom to the actuated side. Here you can see a schematic representation of its workplace. It usually has more than 6 degrees of freedom. However, these result in 6 degrees of freedom on the manipulated object, meaning that once again, in 3-dimensional space, you are able to position and orient an object at any position and any orientation. Here you can see the most common application of delta robots, which is pick and place. Delta robots you can usually not find to have excessive payloads beyond 15 or 20 kilograms. I'm not 100% certain of which is the highest commercially available one right now. And that is due to the fact that delta robots are quite fast, but not necessarily speaking in terms of their velocity, but speaking in terms of their acceleration. So these robots have the highest overall accelerations of the industrial manipulators. Then there are dual arm robots. You've seen that I have placed dual arm robots for SKMs as well as PKMs because I couldn't find an official designation where they actually belong to, because you can essentially read yourself from the base to the mechanical interface, but at the same time you would be able to actuate the same object. That is, if both arms were to grasp the same box, then you would essentially end up with a parallel kinematic machine, as instead if both arms were individually used onto other objects. Its workspace is a perfect sphere, and it usually has more than 6 actuatable degrees of freedom, and this results in 6 degrees of freedom on the object to be manipulated. Let's look into its most common application. Here you can see the Yaskawa Motorman SDA series, which is a dual-arm robot that is most commonly used in human-robot collaboration. A lot of these human-robot collaborative tasks involve the assembly of pieces. Okay, now let's consider the essential difference between PKMs and SKMs. So, a serial kinematic mechanism or a serial kinematic machine is a system of rigid bodies in which each member is connected to 2 other, except for the first and the last member, that are each connected to only one other member. You can think for your arm from your shoulder. Then there are parallel kinematic machines or mechanisms, which are systems where there are 2 members that are connected by multiple joints. For parallel kinematic mechanisms, you can think of your 2 legs being connected to your torso. On the lower side, you find a comparison of SKMs and PKMs in essential performance metrics, such as their accuracy, that is, how close they can position or orient an object with respect to the required position and orientation, how fast they can do that in terms of speed, which can either be velocity or acceleration, the work envelope which they provide, the payload that they are able to handle compared to their own weight, as well as the stiffness that they provide. Stiffness is not only an important characteristic when it comes to the machining of parts, but a higher stiffness helps usually systems to have higher first eigenfrequencies, which usually also makes the operation and control of systems simpler. The most important aspect that we need to point out is that it seems that parallel kinematic mechanisms are advantageous in most of these performance metrics that I have outlined here. But nevertheless, most of the industrial manipulators that you will be able to find are actual serial kinematic mechanisms, such as the articulated manipulators that we have seen before. And that is due to the fact that these are dominantly found in applications that require either precision in big workspaces and are subjected to small external loads. This you can think of the spot welding application of a car, or which don't require any precision in big workspaces and are subjected to high external loads, as for example pick and place applications, where it isn't necessarily important that it is actually positioned accurately within 1 millimeter, but the object that you might want to lift weighs a couple of 100 kilograms. Let's just take common quantifications of these performance matrices. So for serial kinematic mechanisms, you will find that they have a positioning accuracy of around 1 to 5 millimeters, depending on their reach, that is the length that they provide from the base to the mechanical interface. And for parallel kinematic mechanisms, you will find that they have a positioning accuracy of 1 to 2 millimeter, depending on their range. Nevertheless, both of them have a repeatability which is around an order of magnitude higher than their positioning accuracy. And what that means, we're going to look into when it comes to the operation of industrial manipulators. One aspect that is significantly different, as mentioned before, is the work envelope. So we can find that the biggest robot that is currently commercially available offers a reach of about 4 meters, which is the Fanuc M2300, which you can see here on the left, which offers a reach of 4 meters. The parallel kinematic mechanism with the highest reach currently available on the market is the Fanuc M312H, which has a reach of about 1.5 meters. At the same time, the payload of the robot on the left-hand side is around 2,500 kilograms, while this one has a payload of around 15 kilograms. Payload is the term of the object that they are able to lift. However, if at the same time we are also going to compare that to the weight that they have themselves, we can see that the M2300 weighs around 11 tons, while this one weighs around 150 kilograms. Finally, let's look into what it really means to have 6 rotational degrees of freedom or 7 rotational degrees of freedom. So, as you can see in this example, 6 degrees of freedom gives you the opportunity to position and orient the metal pins that are mounted, or in that case, the Fanta cans, to position and orient them to any position or orientation in space, or that is to any pose, which is the combination of position and orientation. Usually, dependent on the design of the industrial manipulator, you will also find that you usually have either 1, 2, 4 or 8 potential solutions to reach these poses. But if we compare this to 7 rotational degrees of freedom, we actually find that for certain parts of the space, well, first of all, this is the first big advantage of 7 degrees of freedom industrial manipulators. They can actually manipulate objects behind a wall, which isn't possible with 6 degrees of freedom. And when it comes to the number of solutions, here it is. When it comes to the number of solutions, you can actually see that 7 degrees of freedom industrial manipulators offer you infinitely many solutions for some poses. That is, you can actually fix the object that you are manipulating in space while moving the rest of the arm out of the way. Funny fact, that is actually the same amount of degrees of freedom that your arm offers you. And if you were to now fix your arm rigidly to the wall, you would be able to see that you are able to maintain your palm in one pose while moving the rest of the arm around. Well, as said before, this is useful because, first of all, you can manipulate objects behind walls, and the other aspect is that if you have tight space, as you may commonly find within the automotive industry, that space is quite expensive, you are able to actually perform more tasks on smaller space, because now you will be able to actually have industrial manipulators avoid one another better than if you were to have solely 6 degrees of freedom industrial manipulators.